And finally, I still have the shaft work plus W dot shaft dt. Okay. So I have, let's rewrite it. What is H minus Ts?
A.
Okay, H minus Ts is G. So, from here follows that du equals, so let me write it clearly here, this is G. So, GdM plus PDS minus P dV, and then I have plus, and I'll write them in red, W dot S dt minus T S dot Gen. We are talking about a specific fluid or solid or whatever. And I'm talking about changing from a temperature, pressure, volume, etc. state 1 to a state 2. Critical concept of thermodynamics. When you go from a state 1 to a state 2, all that matters is the final state. The path doesn't matter. Choose any path you want, you have the same result going from state 1 to state 2. So, you can always go achieve the state that you go from state 1 to 2, putting going through a path that is reversible, and any work could be put in PdV work. That's why, even though in reality you may have shaft work, the process may be irreversible, etc., what defines the state of the system at any time can be written as having the relationship between temperature, pressures, and volumes, and so on. In other words, state variables. These are not state variables, right? The others are state variables. Okay? Having the relationship between state variables without those terms. That's a little bit tricky concept. Jessica, how are you? Okay. There is nothing condensable. And Ricardo is smiling. Okay. Any questions? So, with that concept, I wrote in red because we're neglecting those terms. So, can choose path that is reversible with only PdV work. And then we have the central equation, du equals GdM, and of course for moles, this could be GdM, if I did with moles, plus TdS minus PdV and if I have a closed system, I get two things if I have a closed system. If system closed, dm is 0, and what else happens? Because
dv.
dm is 0, m is constant. And therefore, dm0 means this goes away. M constant means I can divide the whole equation by m. If I divide this term by m, what do I get? U hat. Right? M is constant goes inside a differential. Same thing is going inside the derivative. So you can put that m inside here and you make u over m. Dividing this by m, t is an intensive variable, not an extensive variable. There's no m here. But s over, you can put inside here, s over m is what? S hat. Same thing here. V is intensive, but V is extensive. V over m is what? V hat. So that becomes that actually it's right here, that d u hat equals t ds hat minus p dv hat. Or if we were to divide by n, this can also be g underscore dn. I think I wrote it somewhere. I wrote it. Probably out here. Okay, this term or this term are the same. So closed means dn equals 0, same business, and dividing by n, you can get the alternative molar form. Remember, underscore is per mole. This is an equation that is used over and over and over again. And we can get the dependencies for every one of the energy state variables. So here I have du. How would I get h? Let me write the molar forms. So we have that du equals t ds minus p dv. What would I do for h?
I think dh is equal to du plus.
Well, let's see. Let's get it.
You can just
So
replace the
dh,
H plus PV.
h is u plus pv, right? So that's d u plus pv. So that is equal to du plus the differential of pv. Product rule applies here. So that's du plus p dv plus v dv. But du is t ds minus p dv.
What?
So you get that dh is equal t ds plus v dv. We can do the same thing for A and for G. A is u minus ds. So dA is du minus d of ts. So du, we have it there, is t ds minus p dv. Product rule, minus t ds minus s dt. Dt. Cancel this, and you get that dA is minus p dv minus s dt. And if we finally do G, And we can go either as G equals from the A plus PV, or from H minus TS, either way. Now let's leave the A plus PV. Is the A plus B PV. And you can see here the PV term will become PdV plus VdV. The VdV cancels, so that will be VdV. So those four equations, the four differentials, probably you spent a lot of time with them in Thermo 1. You as students, I believe you had that in your earlier thermal class, so you're okay with all that. Good. And notice a key thing to see here. Usually in problems you change from temperature and volume to temperature and volume, or more commonly from temperature and pressure to temperature and pressure. Notice that if you're changing from temperature and pressure, the independent definite variables are here, the ones that have the differentials, the natural variable there gives free energy. If you're doing temperature and volume, what is the natural variable? That was free. Okay. Any questions? I'll do one example from the book, but I think probably that's enough equations on the board for today. So let's go to Unisync and go a little bit further on that. Now let's see, did I bring a copy of your homework? Yeah, I thought I did. Looks like I left it in my office.
Reminds me of PCM.
What?
This thing.
Oh, it's just from Thermo 1. I remember it pretty well.
We didn't really get this dense in Thermo 1.
No, I didn't. I didn't think you were
So
coming.
sorry I didn't bring power strips. It won't be very long, obviously. We're talking about 20 minutes I have, right? 20, 25 minutes.
15
Let me-
minutes. 10 minutes. 3 minutes.
What are you doing for Memorial Day weekend?
Hopefully not nasty earthquakes.
Going back home. I know that. Well, I think I know that. I'm not really sure.
Is home in Palm Beach? By any chance? Damn it. Do you want to go to Palm Beach?
Why would I want to go to Palm Beach?
So you can take me home.
Nah, home's in the other direction, unfortunately.
Are you going to be here in the fall? Or you got another?
I'll probably be in California.
Nice, dude.
South San Francisco.
Is it with Dow or
And
you got
if you
something
can
else?
save what we did last time, load it up,
And I'll go
I'll keep
again.
using the same.
It's my last term next summer. And I'll graduate in spring of 2018.
So we've done the valve problem. And by the way, let me teach you something else. Some of this convenient is to see some of the values you're interested in on the streams themselves. You can always see them by going, for example, to either the variable directly or to the unit that is next to them and press a worksheet. Then you can see what goes on with the streams and the composition, you see the compositions. But it would be convenient, let's say I wanted to immediately be saying molar enthalpy. Then you can first left click, then right click, and select show table. So this will show on the string, the default is to show temperature, pressure, and molar flow. So left click first to select, then right click, show table. Okay? But I want to be showing molar enthalpy. So what I'm going to do here is that. Go to the table, right click on it, or double click on it, and add variable, and you'll find here, you can find also mass, etc. But let's add molar enthalpy. And molar enthalpy. Okay, so that's the stream in and the stream out. We know it's an isenthalpic process, so the enthalpy and the entropy so as you would expect, the enthalpy is exactly the same, but the entropy has increased. Makes sense. We have expansion as we went to lower pressure. How would I see the other value? Suppose that I wanted to see how much free energy or Gibbs free energy. You have a very primitive spreadsheet within Unison. And HYSYS, by the way. Everything I'm saying for Unison works also with HYSYS. Maybe I will do this another time. So, if you want to make calculations within Unison, right here you see the primitive spreadsheet. So bring in a spreadsheet. Double click on it. If you need more time, tell me.
Is there a way to save a particular table format? Is that like, or will you have to say add entropy, add entropy for every time you make a new table?
As far as I know, you would have to do it. But if you find that there's a way, tell me. All right. So we open the spreadsheet. We put in the spreadsheet, double click on it. I'll show you here that if you parameters is how many columns and rows you have. The default is 4 columns and 10 rows. And go to spreadsheet. So let's say I want to calculate those quantities for stream 1. I would have to import somewhere. Let me put here the state variables that I do have, which are what? I know the pressure. I know the temperature. I know H. I know S. Okay, I should put underscores. Okay, H underscore. You know it's smaller. S underscore. You know it's smaller.